Thank you for the invitation. So, okay, it's recorded. Okay. So I will talk about volumes of odd strata of quadratic differentials. And this is a joint work with Duryev and Yakovlev. Let me start with defining what are quadratic differentials by giving examples. So I will think of a quadratic differential. So maybe let me start with the official definition. So the official definition is that you take a Riemann surface, let's say X. So let me see if I can do, yes. And a quadratic differential is a form that is locally modeled as some meromorphic function times dz squared, where this meromorphic function has at most simple poles. Okay, so this is the quadratic differential Q. And this condition
sorry,
yes.
Are you writing something?
Yes, so you can't see?
Me not.
Ah, okay.
So I don't know about
me neither.
Okay, it usually works. Let me try another thing, because it will be better with drawing. Let me try again to share and just a second. And so, sorry for that. Share. So maybe I will try the screen. Maybe it's better. Let's see. So I try again. Can you see this here?
Yeah, now it works.
Now I do.
Okay, okay. Thank you. Okay, so I take a Riemann surface X. A quadratic differential is locally modeled as f of z, dz squared, and the function f is meromorphic with at most simple poles. So the condition on the poles is such that when you integrate the modulus of q over x, it's finite. So it's an integrable quadratic differential. So this is the definition, but I rather think of quadratic differentials as flat surfaces. So more precisely, half translation surfaces. So you take a polygon in the plane, which has its sides that are parallel and of the same length, and you identify the sides by either translation, as for these red sides here, or half term, as for these blue sides here. Okay. So more formally, a half translation surface is a surface with an atlas of charts where the change of charts are given by this function, so translation and half terms. So this is basically a half translation surface, and it's equivalent to a quadratic differential on a Riemann surface, because I mean, I won't do the proof, but when I draw some polynomial like this in the plane, actually I consider a chart from a surface, and the change of charts are holomorphic, so it's a Riemann surface. And if I consider, yes, question? No, sorry. If I consider, so the plane to be the coordinate z, and then consider the form dz square. Dz square is well glued by change of coordinates like this. So you have to be careful around the singular points. So what are these singular points? So it's singularities of the differential of order k. And you can see that these singularities correspond to conical angles of your flat metric induced by this quadratic differential. So let me work on this example to show you. So here at the vertices of the polygon, you may have some singularities of the flat metric, which is just the Euclidean metric induced from this drawing on the Euclidean plane. So what are these singularities in this case? So if you look at this point, for instance, you see that the cone angle on this point is just pi, because I just glue by half term. And here again, it's one conical singularity of angle pi. You can also compute the cone angle here. So it's a small computation, small exercise, and you can show that it's 3 pi. And this one also. Yes. So I hear some. Okay, I don't hear completely right. So if you have question, maybe either I can also open the chat if maybe that's help. Sorry, let me just. Okay, so then I have the chat. Okay, so here the surface has 4 singularities of angles 3 pi, 3 pi, pi, and pi. Okay, so this corresponds to singularity of the quadratic differentials of order 1, 1, minus 1, and minus 1. So basically the formula. So it's a small complex geometry computation to check that the conical angles that you get for the flat metric correspond to this, are equal to k plus 2 times pi, where k is the singularity order. Let me give another example. This is a very special polynomial made out of 3 squares. So it's called a square tile surface. And here, if you do the same computation, so here you get, so this is only one point on your surface. And when you turn around this point following the identification, you get an angle. What is the angle here? 4 pi. So this is easier as an exercise. Okay, and here at the bottom, you still get an angle pi here and angle pi here. So you have a quadratic differential with singularity of order 2, minus 1, minus 1. So of course you have some, for instance, Gauss-Bonnet formula or Euler-Poincaré characteristic formula that gives you a relation between the singularity order and the genus of the surface. So here, this example is of genus 1, since the sum of singularity order is 0. And I think this example is also genus 1. Okay, so from now on, I will think of quadratic differentials as half translation surfaces, so polygon with identified sides with translation and half terms. Okay, questions on this definition? Then let me introduce some notation. All right. So now I consider only odd singularities. So k is a vector of integer ki that are odd and positive. They are also allowed to be equal to -1. They are the singularity order of the quadratic differential that I will consider. And then I consider the stratum of all half translation surfaces with this kind of conical angles. Or if you prefer, the strata of quadratic differential with this singularity order. Modulo the operation of cutting and pasting the polygonal pattern that I have. This is actually a complex orbifold of dimension d, where d is just 2g minus 2 plus the number of singularities. Let me say a little bit more about this fact. So actually, this set of quadratic differential, when you fix the singularity order, has a nice system of coordinates, of local coordinates. The local coordinates, you can think of them as, if I consider the model as polygon, sorry, you can think of local coordinates as the sides of these polygons as complex numbers. Looking only at the independent sides of this polygon, you get a certain number of complex numbers, and this is, you can think of this as your local coordinates in the stratum, in the family of all half translation surfaces. More formally, if you want really to construct these local coordinates, when you what you consider is the periods of your quadratic differentials. What are these? Okay, so let me say it slowly. So,
all right, I missed what is L of K in the formula. L graphic of K. 2G minus 2 plus L of K.
L of K is the number of singularities.
Ah, the number of singularities. Thank you.
R. Yeah.
I don't know how to, like, it's the number of
R.
Number of singularities.
K is this set of order singularities? Yes, order. Yeah.
So just what is what is called R in this sequence? K1, K2, KR.
Yeah, it's any sequence of odd integer and possibly minus ones that sum up to 4G minus 4. Of course, you always have this condition.
The question is it right that L of K is equal to R or not?
Yes. Sorry.
Yeah.
Yes.
Okay.
Yeah, maybe it's
Okay.
yeah, it's yeah. So what is this contraction? Is so you consider you can forget about this contraction if you are happy with the definition with the polygon, but you take the double cover that lift your quadratic differential as a global square of a holomorphic differential, abelian differential. And in this double cover, you have an involution that exchange the two sheets of the cover. And you consider only the anti-invariant part of the relative homology relative to the singularities, to the points. So only the anti-invariant part with respect to this involution. And this is a model for your strata, a local model for your strata. So these are the periods or the local coordinates for your strata. But you can really think about the size of the polygons. It's okay. So it happens that once you look at these local coordinates and you look at the natural Lebesgue measure on these coordinates, this Lebesgue measure is preserved by a change of coordinates. And this is, I think, a result of Goujard and Masur. So it defines a measure on the stratum. Okay. So locally, it's just Lebesgue, but it's well defined globally. And then you can define the Masur-Veech volume of the stratum like this. So this mu is this Lebesgue measure. So what is this formula? So you consider only the surfaces of area less than 1. So actually, if you interpret the integral of Q over X in terms of the flat geometry, it's just the area of the surface, the area of the polygon. Okay, so if you restrict to surfaces with bounded area, then the measure of the set is finite. So this is a result of Masur and Veech. And then you can speak about the volume of strata. It's this definition. Okay, so once you can measure something finite, now you want to compute it. And what is the way to compute this volume? It's just to count integer points or rather rational points, if you prefer, in the set of surfaces of bounded area. So let me give the result. I mean, the volume can be computed as the limit as the number of square, big N. So big N will be the number of squares. Oh, no, sorry, it's too soon, maybe. Oh, yeah, okay. So, okay, let me say first the thing. So integer points in the stratum just correspond to square tile surfaces. Why is that? So you want to think of quadratic differentials with integer periods. So in the model of polygons, it means that you want that the sides of the polygons, so let me do a small example here. You want that the sides of your polygon to be integer, meaning to belong to the integer lattice in the plane, right? So it means that maybe you want these points to belong to a rational lattice in the plane. So we should have some rational lattice here. Okay. Okay. I'm just trying to draw a square tile surface. Sorry. Okay, so it's just by the definition of the local coordinates that integer points correspond to square tile surfaces. So what you want to count is actually square tile surfaces. The area of square tile surface is just the number of squares. Okay. So basically what you do is you count the number of square tile surfaces with at most n squares. So this is exactly this thing here is just the number of square tile surfaces with at most n squares. So sorry so this is the notation for square tile surfaces. Okay, and so you evaluate this number. You look at the behavior as n goes to infinity. It should have some constant times n power the dimension of the stratum, because this has dimension d. Okay, and this constant basically gives you the volume. Yes. Questions?
Is it always possible to rearrange the cuts so that they always be either vertical or horizontal? What do you mean?
Is it? I don't understand the beginning of the question. Sorry. Could you?
So in your example, the vertices are integer, but the cuts are not vertical, neither vertical nor horizontal. But I wish to have just
what? So what I call integer is like this complex number here is an integer, meaning that it belongs to the lattice z plus iz. This is what I mean by integer.
yes, but is it possible to represent the same surface in a different way so that all cuts will be either vertical or horizontal? So I just cut off small triangle on the left and put.
Yes, I can. Yeah, sure. I can put this side here. Is that what you want? Like I can cut and glue, so I can always represent sides that are, but I introduce false singularities. So let me maybe precise what I mean. Let me draw another picture for the same surface. And I hope that it's not too small, sorry for that. So here, this is this side. Here, this is no, sorry. This was the last singularity that I had here. Okay, so I think this is the same picture where the gluings are a little bit different. So this is this. And so I just really cut and glue these two pieces. Okay, so the identification are a bit different, and I introduce false, like it's not really singularities, it's flat points with no singularity, but they appear at the vertices of the polygon. And you have to do the gluing carefully so that this, for instance, I didn't precise the gluings to begin with. So maybe this was like this, and this was. Oh, I sorry, my picture begins to.
Okay, thank you.
Yeah, but yeah, you can do it, and yeah, but yeah, you can always cut and glue, so you can always put your vertices on the grid if you wish. So I don't know if, but it doesn't mean that this period, which is really measured between two singularities, it's not vertical or horizontal. Or maybe I didn't understand your question. Maybe you want to ask, is there any other surface in the same stratum that have this vertical and horizontal periods, maybe? So the answer is yes. You can always shift a little bit. You can apply some twist and shift a little bit this to get really everything, every period vertical or horizontal. So I'm not sure that I understood your question.
You know, this is what I mean. Yeah.
Okay. Sorry. Okay. Other questions? Okay, so now I will forget a bit about all this setting and concentrate on the goal of computing volumes of strata of quadratic differential with odd singularities. So the purpose of this slide is just to show you that for that, I just need to count square tile surfaces, basically. So of course, the square tile surfaces that I want to count have specific conical angles. This is the thing that I have to deal with. So let me do a brief history about the computation of volume of strata of differentials. So the first results were produced by Eskino-Kunkov, and they use like Hurwitz theory and representation of the symmetric group to compute volumes, I mean, to build algorithms to compute volumes of strata of small dimension. And then this work by Asweya, Eskin-Zorich give closed formula for all volumes for genus 0 surfaces. And this is more using dynamics on the moduli space. So I won't extend on that for now. The result of Delecroix, myself, Zograf, and Zorich is the result that we extend in this talk. So it's a result about principal strata only. Principal strata means that we consider only singularities of order 1 or -1. So simple zeros or poles. And we express the volume of this strata as a sum over stable graphs. So you will see that the formula that we prove has the same form. It's a sum over stable graph. So I will define everything. And building on that formula, these 7 authors show that actually the Masur-Veech volume of the principal strata satisfies some topological recursion. So they just recognize that our formula was some was induced by some topological regression in some sense. So there is also work from algebraic geometers, because you can also compute volumes in other ways by looking at volume form and trying to find algebraic classes that represent this volume form, etc. So this is the work by Witten-Kontsevich. So they are able to express this volume as some Hodge integrals. Okay, and there is a lot of results. Also, Amol Agarwal, and I will say more about this result later, was able to compute the asymptotics as the genus tends to infinity of these volumes based on this formula also. Also based on, sorry, so this is different. This is based on the algebraic work. So this is based on the formula as Hodge integral. Kazarian and Yang-Zhang were able to derive a quadratic regression for the volumes based on this work. Okay, and there is a work which is not which is in progress, I think, by Masur-Veech, that gives a regression for odd strata. Okay, so a lot of work, and the formula that I will present today is the generalization of the work of Delecroix-G-Zograf-Zorich myself. So here is the formula, and I will spend time explaining it in detail. So there is, sorry for the formula, but I will go into detail. So this is just a definition. So this volume with a bar is what I will call the completed volume of the stratum. So it's not quite the volume of the stratum that we want, the Masur-Veech volume that we want to compute, but almost, and I will explain. So I define this quantity as a sum over some stable graphs So what are stable graphs? Stable graphs are just graphs with some decoration that can have loops, that can have also legs. And the decoration is by some genus. And also by some vector k. For each vertex, you will have a set of integer k, k1, maybe k2, etc. So this is a stable graph. So it's a decorated graph. I will say more about that in a minute. Here, what you get here is a polynomial. So the bi's are the variables. For each edge of this stable graph, I assign a variable. So here, let's say I have one variable b1, one variable b2, one variable b3. So here, this factor is just the product of all these variables. Here, we get the product over all vertices. So these are the edges, these are the vertices. And on each vertex, I will define some polynomial, and I will define it later. So on each vertex of this graph, I get a specific polynomial in the bi, and I consider the product of all these polynomials. So this is just a big polynomial, and I divide by the cardinality of the automorphism of the graph. So this is a polynomial that depends on the graph that I call P gamma. And then I apply some linear operator. So what is Z doing? Z is linear, and Z is taking a product, a monomial like this, to a number which is the product of zeta values of mi plus 1 times this mi factorial. And in what follow, the mi will always be odd. So this is the data value at even integer. Okay, so it's just a rational times an even power of pi. Okay, so this is the quantity that I define. It's a sum over stable graph of some linear operation that I do on some polynomial that depend on the graph. I will do a complete example in the next slide. So for now, this formula says nothing. I just define this. And the result is here. So the completed volume is actually the volume, the Masur-Veech volume that I really want to compute, plus some additional contribution. And this additional contribution are an explicit combination of volumes of boundary strata. So let me maybe show you on an example, and I will explain later why we get that, etc., how we get that. So is this definition kind of okay? Are there some questions before the example?
Water is a boundary strata you're considering.
Volume of
Q. Some specific boundary strata are they, or?
Yes, they are. It's very specific. Yes, and I will extend more on this term later. So there is an explicit formula for this coefficient for the set of odd k prime that appear, etc. So everything is explicit. So let me forget that for just to begin with, and I will detail that later. Okay, so let me do an example by just applying this formula in some stratum. So the stratum that I want to consider is the stratum with one singularity of order 3 and 3 poles. So here, these are all these constants that appear in the formula. Just normalization constant. The dimension of the stratum is 4. And I need these 4 polynomials that I will define later, but I just for now, I just give you the values of these 4 polynomials. So let's apply the formula. So what we have to do is to do the list of all stable graphs corresponding to this stratum. So this is done on the left. So here I claim that I have all stable graphs that correspond to this stratum. You see that, so this stratum corresponds to surfaces of genus 1. And here, once you sum up the genus of the vertices and the number of loops, you get also 1 here. Okay. And then I distribute the singularities on each vertex. So here there is only 1 vertex, so all the singularities are here. Here there are 2, so I need to distribute these 2 singularities, etc. Okay. And of course, I will explain where these stable graphs come from, etc. So let me just apply the formula. So for each stable graph, I have a polynomial. So the polynomial have a term which is just the product of the the variables, so B1, 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 B2. So this is the easiest term. And then for each vertex, I get this polynomial. So what you can see is that I apply to each vertex the polynomial in the variables that I see that correspond to the edges adjacent to this vertex. So here, these two edges are labeled by B1. So I just put these two variables, B1, B1. Here, nothing complicated. I have two vertices, two polynomials. I see only one incoming edge labeled by B1. And here you see, for instance, here, this polynomial corresponds to this vertex. And I have one variable B1 and two variables B2. Okay. And the polynomial, I mean, you need the decoration of the graph to get the right polynomial. Okay, so
and 2 in the denominator is the order of the
yeah, it's the automorphism of the graph. So here, here you get this exchange of the two half edges, if you want, and here also you get this this automorphism too. Oh no, sorry. Oh no, this two is this one. Sorry, I'm sorry. This two is this one, and over two, I think it's just a global factor. So let me go back to the. Oh, sorry. So yeah, this two is just a global factor. So the 1/2 is just the automorphism of the graph. And then what remains to explain is this factor 3. So here, all these singularities are labeled. So in particular, you have 3 poles with 3 labels. And when you consider stable graph, actually you have 3 ways to label this pole, etc. So actually with the labels, you get rather 3 labeled stable graph instead of just one that I do here. So here you get a polynomial. Let me just do this example. I think the polynomial is yes. Questions? So if I compute this term, I get this polynomial, which is B1 over 3 over times 8. So I apply just the linear operator V, and I get 24 zeta of 4. Okay, and I do the same for each, and I think I also need to multiply by this constant. I do the same for all stable graph. I get 3 numbers that I sum up, and then I get that the completed volume is this sum, 2 pi 4 over 3. So it's not the volume of the stratum, because the volume of the stratum is pi over 4 over 9. Okay, so you have this additional term. And this additional term, I claim that this is the volume of the stratum Q minus 1 to the 4, so 4 poles and genus 0. And H0 is the strata of abelian differentials with 1, 0 of degree 0. So when I put the letter H is to talk about abelian differentials, so holomorphic one forms. Okay, if you prefer, you can think of quadratic differentials that are global squares of holomorphic one forms. Okay, so so it's a bit intricate, but could you see how the formula works? Are there some questions just about the formula, how it works? And if not, I will. Yes.
What is a 0 of degree 0?
And sorry, I can't hear you very well. Could you repeat, please?
These are abelian differentials having 1 0 of degree 0.
Yes, 1 degree of 1 0 of degree 0. It's a genus 1 surface with it's
so
just
no zeros at all, just a mark point.
Yes, just a mark point. And it will be clear when I will do the example completely, I think. So let me go into that. And to go into the proof of this formula, I need to speak about ribbon graphs. So what are ribbon graphs? Ribbon graphs are just, I mean, there are several ways to define ribbon graphs, but you can think of them as graph embedded in surfaces. So graph with a tubular neighborhood, if you want. Okay, so for instance, these two graphs are just the same as graph. It's just this graph with two loops and one other edge, but they are different as ribbon graphs. So here, this is an embedding of this graph in the plane or in the sphere, if you prefer. And here, this is an embedding of this graph in a torus. So they correspond to distinct ribbon graphs. Another way to encode the ribbon graphs is to give a cyclic order of the half edge at each vertex. So this is equivalent to embed the graph in the surface. Okay. So actually, ribbon graphs are related to quadratic differentials or half translation surfaces in the following way. So here I consider Jenkins-Strebel differentials. So what are these differentials? So first of all, they are quadratic differentials. But here I allow double poles. Okay, so in this setting, I allow quadratic differentials to have double poles. In the flat picture, in the polygonal picture, if you want, it corresponds to infinite cylinders, infinite Euclidean cylinders.
Double poles at the punctures, yeah?
Yes, exactly. So at the punctures. And when I say Jenkins-Strebel, I just mean that all horizontal leaves, or the leaves of the horizontal folation defined by the quadratic differential, they are just all closed. I don't speak about the singular one, but the regular one, they are just closed. All trajectories are periodic, if you want. So this is what I mean by Jenkins-Strebel differentials. Basically, it's a half translation surface with possibly half infinite cylinders that you can glue. Okay. And this, by a theorem of Strebel, corresponds to ribbon graphs with metric. So I define the ribbon graph. What is a metric ribbon graph? A metric ribbon graph is a ribbon graph with a data of a length for each edge. Okay, so for each edge I assign a length, and this puts a metric on the ribbon graph. So what is this correspondence between Jenkins-Strebel differentials and metric ribbon graphs? Oops, I need to erase that. it's given by Strebel theorem that says that if you take a Riemann surface with n punctures and genus G, and you take a set of lengths, B1, Bn, then there exists a unique Jenkins-Strebel differential, so quadratic differential, with double poles of residues like that. Okay. And considering this Jenkins-Strebel differential, I can look at the critical graph of this differential. So the critical graph is the set of horizontal leaves that pass through the singularities. So it's a graph, and it's a graph on a surface, embedded in the surface. So it's a ribbon graph. And then it's also a metric ribbon graph, because here you have a flat metric, so you have a notion of length for each curve here. Okay. So this correspondence actually defines a homeomorphism between the moduli space of Riemann surfaces times the parameter space for the lengths of the faces to the combinatorial moduli space, so the set of all ribbon graphs, metric ribbon graphs of genus G with n faces. Okay. So yeah, I hope that it's clear what I call by length of the face, the length of the face here, B2. Once I put a metric on the graph, the length of the face is just the sum of the length of the edges. So B2 here is just L1 plus 2L2 plus L2, etc. Yeah, so yeah, I can think of a ribbon graph as a quadratic differential if I wish. Okay, so this is the story. And I get this homeomorphism. So you need to be a bit careful if you want to extend this homeomorphism to the natural boundary of the moduli space. So here, there is a natural compactification of the combinatorial moduli space by so-called stable ribbon graphs. Okay, I won't go into details for that. And here, this is the Deligne-Montfort compactification of the moduli space of Riemann surfaces. So you can try to extend this to this compactification, but you have to be careful, and it's not really this compactification that you have to consider, but rather a quotient of this compactification. But again, I won't extend on that. Okay, so let me define now these polynomials that appear in formula. And for that, I need to define the coefficients of the polynomial. These coefficients are some intersection numbers defined as following. So in the combinatorial moduli space, which is a set of all ribbon graphs, you can look at the subset of ribbon graphs with fixed valencies. Like the vertices have some fixed valencies. For instance, vertices with odd valencies. Okay. For each subset where you fix the valency of the vertices, you can show that the components of these sets, I mean, this is basically what Kontsevich does. I don't know why I don't put the name here. So Kontsevich showed that on each component of this set, you have a natural orientation, which allows you to define the cycle in the compactification. And actually, a homology class on MGN bar if you are careful enough. Okay. So the intersection numbers that I need are just the intersection of the psi classes along this homology class. Okay, and if you don't know what are psi classes, etc., it's not a big deal because I will explain how to compute these numbers, what I use about them, etc. So I don't want to define properly all these numbers. But here is what I call the Kontsevich polynomial. It's just a polynomial with these coefficients. So if you don't fix any constraint on the valency on the vertices, instead of this class here, you just replace this by mgn bar, and you get more classical intersection numbers that are Gromov-Witten invariants, etc. A lot of things are known about these numbers, but less things are known about these restricted intersection numbers. Okay, so this is the Kontsevich polynomial. Let me look at the time, yes. Let me say a few words about the relationship between this polynomial and the count of integer metrics on ribbon graphs. So basically, what Kontsevich showed is that this polynomial actually gives the number of integer metrics on ribbon graphs with this fixed valency profile, if you want. So here I define this as a polynomial of homogeneous polynomial of degree 3g minus 3 plus n minus big M. And here I will also explain this is not usually a global polynomial, but I will explain later. And here these are up to lower order terms. Okay. Okay, I have a few things to say about this. So before going to the explanation about these results, I think I want first to explain how to compute these intersection numbers. So, sorry, are there any questions on this formula yet?
Yes, probably comment. I think Kontsevich has nothing to do with integer numbers.
Okay. What do you mean?
There was nothing about integer values, so he always considered a symplectic form based on these numbers. So there was nothing about integer b's in Kontsevich paper of 92. I'm pretty much sure about that.
So you mean, I think still he considered yes, I mean, so this is not really like, it's not formulated like this, of course, in the Kontsevich paper, but I think the main formula of the paper is just the Laplace transform of this.
Yes, but Laplace transform of integers would be not, it would be some exponentials, e lambda minus 1. There will be different times. For discrete Laplace transform, and I believe I was the first who did it about the same time.
Okay, sorry so I should correct my slide. Okay, thank you for that. Okay, so sorry, I will check the.
Yes, please.
Thank you for the remark. Okay. Okay, let me and you will. If I am wrong, sorry. Let me just try to tell you how you can compute these coefficients first. I mean, there is a algorithmic way to compute it. So let me just say a few words about that. So you can put these coefficients into a generating series where you record the, oh, did I introduce the notation tau? Yes. Yes, okay. so when the t variables encode the power of tau, and the s variables encode the valency profile. Okay. So basically, what you want to do is to compute this generating series. So the first remark is that if you consider the specific point 0, 1, 0, 0, 0, you recover the classical generating series for intersection numbers with no constraints. Okay. And if you want these coefficients, you just need to compute the t derivatives of this generating series. If you look at this formula, you can also believe that these coefficients are just obtained as computing s derivatives of this generating series and evaluate at this point. Okay, this is a small observation. Okay. I think that Kontsevich showed that this generating series is an asymptotic expansion of a matrix integral. So this gives a recursive ways to compute these coefficients. And actually, so I think this is just yes, sorry. Okay, and actually the reason that I used to compute these coefficients here are the correspondent of Dixon-Zuber. So what this says, it basically says that there exists some explicit and some linear isomorphism that you can really program and compute between the polynomial in t derivatives and the polynomial of s derivatives, such that so when you look at some get it straight, when you look at t derivative of these generating functions at this point, it's a linear combination of s derivatives of the linear function at the same point. Okay, so you have some linear relation between the, I mean, it's not linear because you get some polynomial inside. So, and this is the exponential generating series, but you get some relation between the classical intersection numbers and this one. Okay, so all of this you can put in your computer and compute the first coefficients easy. Okay, so this is just one word about that. And now let me say a word about the polynomiality. So it's actually a more general fact that when you count metrics on ribbon graph, you get something which is maybe not a polynomial, but a piecewise quasi-polynomial. So let me just say a few words. So let me consider an example. So here I drew a ribbon graph. So I really think of it as a ribbon graph, so embedded in the plane. So I put the length of the faces bi, bj, bk, and I should also put some lengths on the edges. Let me try to. So the L1, L2, L3 are the lengths on the edges, and the bi's are the lengths on the faces. So what are the relations between these lengths? So the face B, so the length bi is just equal to L1 because there is just one edge on the face. If you look at bj, the length of the face bj is L1 plus L2, and bk is L2 plus 2 L3. Okay. So basically, if I give you the set of lengths of the faces, and I ask you how many choices you can put for the Li, for the length of the edges, what you have to solve is a linear system with some very specific integer matrix, okay? And you want to get the integer solutions of this linear system. So once you look at the set of lengths that satisfy this equation, this is naturally a rational convex polytope. And when you want to count metrics on such ribbon graphs, what you are looking at is the number of integer points in this polytope. Okay, it's the number of integer solution of this equation. Okay, so this is a classical result about polytope, that the number of integer points in a rational convex polytope is a piecewise quasi-polynomial. So when I say quasi-polynomial, it means that the value of the polynomials depends on the parity of the BI. Okay. You can also look at the volume. So there is a natural volume form on polytope. So you can speak about the volumes of polytopes also. And this is classically known as to be a piecewise polynomial. So the result is that actually when you are outside the walls, so in the chambers, and if you look only at the higher order terms of all these polynomials, so this polynomial with these coefficients that are intersection numbers, etc., is just equal to the sum of over all ribbon graphs of the volume of this polytope, and it's also equal to the sum over all graphs of the number of integer points, to the count of integer metrics. So actually, this is always equal for the higher order terms. I mean, the number of integer points is asymptotically the volume of the polytope when you consider big lengths BI. Okay, so yes, so the problem is really what happened on the walls. This is the question. Okay. So let me do a small computation as an example for the polynomial N03 with singularity 3 minus 1. Sorry. Okay. So if I look at the formula that I put here, this is what I want to count is the number of integer metrics on ribbon graphs with this singularity data. So let me go back to the example. So I want ribbon graphs of genus 0 with 3 faces. So this is this number 3. And I want this singularity data. So I always have to add 2 to get the valency of the vertex. So 1 vertex of valency 5 and 1 vertex of valency 1. Okay. Let me clear everything because so this is the polynomial that I want to compute, which is just the number of integer metrics. So I first have to do the list of all ribbon graphs with this data. So I need 1 vertex of valency 5 and 1 vertex of valency 1. So I get these 2 possibilities. And now I put a length on the faces, and I want to know how many choice of lengths of the edges there are for each case. So I think here I wrote already the equation to determine the lengths, L1, L2, L3. And actually, when you solve this linear system, you see that you get one solution inside this chamber. So this chamber is Bj smaller than Bi plus Bk and Bj bigger than Bi. This is the equation of this chamber. Okay. So to be able to choose L2, for instance, you need Bj to be greater than Bi. Okay, etc. Here you can do the same computation and you get two.
Sorry, Bj should be greater than Bk.
Bj, no, here, no. So let me rewrite the equation. So here L1 is determined by this equation, and then L2 is determined, I mean, at the condition that Bj is greater than Bi. And then if you subtract everything, like L2 is equal to, so if I solve this, let's solve this. L2 is equal to Bj minus Bi. So you need this condition so that it's positive. And L3 is Bk minus L2, so minus Bj plus Bi over 2, and you still need this to be positive. So this gives you this other concept, right? So yeah, I mean, it's painful to do this computation for more complicated example, but you can do it by hand for small examples like this. Why not? So, okay. So now you have to sum over all possible permutation of ijk. So here in the simplex B1, B2, B3, I draw the total contribution of all this count of integer matrix. So what you can see is that in all these chambers here, like this, etc., and inside here, the contribution is 3. I mean, it's basically 2 plus 1. Okay, but if you look at the walls, like the hyperplanes of equation, for instance, B2 equal B3, here, the contribution is not 3, it's 2 or even 0. Okay. And what you get when you compute this polynomial, you get the value in the chamber, which is 3. So I did this example to show you that the number of integer matrix on this graph is almost everywhere 3, but there are some walls where it's not 3. Okay. And actually, when you want to replace everything by 3 here, what you add on the walls is a count of integer matrix on some degenerated ribbon graphs. Okay, I'm looking at the time. Yes, so I still have 20 minutes, right? Okay, and you should stop me if you are if you are tired by this. The difference between 3 and the count of integer matrix is the contribution on the walls. So if you look at what happens when, for instance, here, when B1 equals to B2, so I should put some B1 equal to, yeah, B2 here, B2 and 3. So I'm looking at what happened here. In that case, if you look at the limit where B1 equal to B2, it means that this edge have length going to 0. Okay. And what you get at the limit is just this graph, which is now disconnected because, I mean, basically you pinch this loop, and now you get some, this is disconnected, and you get a union of two ribbon graphs. And basically, the difference between the 3 and the 2 here is the count of metric on such degeneration. So this is what we want to address more generally for all the cases. Questions on this example? Okay, let me put all of this together and show you how we prove this formula, where it comes from, etc. So let me recap everything. So we want to compute volume of strata of quadratic differentials. So I first say that to compute volumes, you just need to count integer points in the stratum, and these integer points correspond to square tile surfaces. What you want to do is to count square tile surfaces with at most n squares and let n goes to infinity. So the first step, which is the same step that we did in the work with Delecroix-G-Zograf-Zorich, is that you take a square tile surface. So let's pretend that this is a square tile surface. You can imagine a grid where it's drawn here. And the first remark is that when you get a square tile surface, it always decomposes into horizontal cylinders. So it makes sense to speak about the horizontal direction. And I mean, when you look at what happened for the horizontal foliation, you can always, how to say that? Like the horizontal leaves that do not pass through singularities are always regular and always form some ring, some cylinder in the surface. And since you get all square tile surfaces, I mean, you can always decompose this surface into these bands of square, if you prefer, that correspond to horizontal cylinders. Okay. So now I want to encode this decomposition into cylinder in some graph. So this is the final stable graph that I want to encode this. So there are several ways to define this stable graph. First of all, I can think of so this is maybe the picture for this surface. So I just glue everything and I get this topological picture. I mean, it's almost a flat picture, but I mean, I hope that it's kind of clear. Okay, so this is here you see the yellow cylinder, which is glued to itself here like this. And here, this is the blue cylinder, which is glued to the yellow one. So one way to define the stable graph is just to pinch the west curve of the cylinders. So pinch this curve. Then you get a stable curve. And you take the Joule graph and it's a stable graph like this. Or if you prefer, if you don't know about the Riemann-Montfort quantification, you just take the graph where edges are cylinder, edges correspond to cylinder, vertices correspond to the graphs that correspond to the boundary of the cylinder. So each cylinder is bounded by one or two critical graphs of the quadratic differentials. Actually, it's ribbon graphs because it's always a graph in the surface. So it's ribbon graph. So each vertex corresponds to a boundary of the cylinder. And I mean, you glue everything accordingly. And the half edge, so I should say, what are the half edge? The half edges are just the poles. Okay, so here I get two singularities of angle pi, so 2 poles of the differential, and I want to record them like this. I mean, it's optional since it's already recorded here. So here I put the genus of the ribbon graph that I get. Okay, so here it's this ribbon graph. If you look at the red graph here, it's genus 0. Here it's genus 0 also. So this is just the genus of the ribbon graph that I get. This is just the degree of singularities that I see on the ribbon graph. So if I add 2, it's just the valency of the graph. So it's 5, 1, 1, 1. Okay. And the BIs are just the perimeter of the cylinder. They're just some numbers. And I put them as variables on the stable graph. So I claim that I can encode the decomposition of cylinders by this decorated stable graph. Okay? And basically it corresponds to pinching each cylinder and looking at the corresponding stable differential that I get, basically. So for each type of decomposition, for each stable graph, what I want to do is to count the number of such square tile surfaces. And to count the number of such square tile surfaces, I have to evaluate how many choice of parameters, like the heights of the cylinder, the twist of the cylinder, the length of each these segments. Are there some questions? I could hear something. Okay, so basically, I mean, you have to write things carefully, but basically the problem is reduced to counting the number of metrics on this ribbon graph. I mean, what is the most annoying to compute is the number of choices for the length of all these edges. Because all the other parameters are easy to control in a sense. But what you want to know is what are the choices that you have for this length, L1, L2, L3, etc. This is L2, L4. Okay, and basically, I hope that it makes sense now. Basically, what you want to do is to count integer metrics on ribbon graphs. Okay. Once you fix the cylinder perimeter, so it's also the length of the faces of this graph, B1, and this is B2 and B2. What you want to evaluate is the number of choice of lengths for the edges, number of integer metrics. Okay, so I hope that now the first big term in the formula makes sense. And if not, please ask questions.
Why do you work with only odd orders of the zeros?
No, I allow poles also. So -1 singularities.
Mm-hmm.
Or did I understand your question? Sorry.
Why even orders are not allowed?
Why even? Why not even?
Yeah.
Because it's really painful to count integer metrics on graphs with even valencies. Maybe I will do at the end an example of what is the problem with graph with even valencies. So first of all, we don't have a nice formula for the polynomials that count these metrics. And also they are only defined on some hyperplane naturally when you get even valencies. So it's a bit more painful. But we hope to do something, but it's a bit more complicated. Okay, let me finish, okay, with going back to the example, yes. Okay, sorry, it took me longer, sorry, that I expected. Okay, so let me, yes, we've seen this example before. So let me just say one more thing. So now you understand that each stable graph encodes a decomposition of your square tile surface into cylinder. So here I draw the topological picture that corresponds to the corresponding square tile surfaces. So here you get only one cylinder, which is glued along this ribbon graph. Here you get one cylinder, which has one boundary here and one other boundary here of genus 1, etc. So each contribution to the volume comes from a different ribbon graph. Let me just look, because I want to, yeah, okay, I want to finish it. Let me say now a few words about these additional terms that we get. Maybe it's now clear why we get additional terms, but let me give you first the formula. So if you remember, the formula that I gave at the beginning is that something that I defined as the completed volume, so the sum over stable graph, is equal to the volume of the strata plus some additional terms that are some other volumes. So what are the coefficients in this formula? So it's really, I think it's really nice, because it took us a while to determine these coefficients, and they were so simple at the end that it was really a nice story. So what is this formula saying? So you just formally declare that your completed volume is just some product of some, let's say some vectors, if you want, k1, kn. You see just that as some vectors. And you do the same for the volume of the product. Okay. So here there are this bar, so these are not the same vectors, okay? And I claim that the coefficients in the formula are just given by some change of variables, if you want, by replacing each one of these vectors by the one without bar plus some additional contribution, which is very explicit, which involves this double factorial, okay? And if you look at the example for just the class of 3, the completion of 3 is just 3 plus 1 times 0 times minus 1. So let me show you how it worked in the example that we did. What it means is that for the stratum 3 minus 1 to the 3, okay, so I should write something else. I should write that the completion of minus 1 is just minus 1. So to compute the volume, the complete volume of this stratum, what you do is you consider individually each singularity, and you replace by a linear combination. So each minus 1 I just replace by minus 1, and the 3 I replace it by 3 plus 0 and minus 1. So it gives, I mean, it translates exactly to this formula. Okay, so here the coefficient is really simple, it's just 1, but in general, the coefficients that you get are just some double factorials, some linear combination of double factorials. Okay. So there is some kind of miracle that gives you that this special linear combination gives you what you computed before. Okay, so now the explanation that makes sense now that I presented the proof. So we computed the volume of 3 minus 1 to the 3. At some point, you see this stable graph. This stable graph encodes surfaces with 2 cylinders. Okay, maybe I think I should maybe do this picture again. And so here, I think it was like, okay, maybe I'm not able to, let me, yeah, this is this case, yes, okay. Sorry. Okay, so you have these two cylinders, and one of these cylinders is bounded by some ribbon graph like this. Okay. And we've seen that when you compute the number of integer matrix and you replace by the polynomial, the things that you add is the contribution of this degenerated ribbon graph. The ribbon graph obtained when you pinch the red curve. So if you look at what you get in your global counting of square tile surfaces, now you have counted additional square tile surfaces that are now disconnected. You count additional square tile surfaces with I mean, there is one surface that corresponds to one cylinder which is glued to itself here. So along this graph, and there is another cylinder which is closed and which gives you another disconnected surface. Okay, and here this is, I claim that such a square tile surface belongs to the stratum H0. So it's an abelian differential of genus 1 with one mark point. This is the mark point. And this is some surface in the stratum Q minus 1 to the 4. Okay, so looking at this degeneration of ribbon graphs, what you get in your global counting is count of square tile surfaces, I mean, disconnected square tile surfaces in some. Okay, so I think, I'm sorry, I took too long. Okay, my time is up. Let me just try to take 2 minutes, if it's okay, to show you what I want to do next. I mean, why we do all of this.
Absolutely okay.
Okay. So, as I said before, this work generalized results of Delecroix-G-Zograf-Zorich for principal strata, and using this kind of formula, like sum over stable graphs of some polynomial, etc., we were able to prove a lot of asymptotic properties as the genus of surfaces tends to infinity. So let me give a few examples of these asymptotic properties. So the hope is that we can prove the similar things for odd strata also. Okay, so what are these properties? For instance, we can look only at square tile surfaces that have only one cylinder. And either when you cut along the cylinder, it separates the surface or not. So you can differentiate between the surfaces with one cylinder, which is separating or not. And when you look at the contribution of separating one cylinder with respect to non-separating ones, I mean, the contribution in the volume, and you let the genus tends to infinity, you can compute the ratio and show that I mean, basically, we say that with very low probability, the cylinder will separate the surface. Question?
Could you explain what do you mean by one cylinder surface?
One cylinder surface is a square tile surface that has only one cylinder. So it could be, I don't know, could be several stuff here. So maybe I'm not able to imagine something. Okay. Let me try to find something.
Thank you.
Yeah, okay. Okay. Another thing that you can do is you can look at surfaces that have only one cylinder with respect to all other surfaces and look at the proportion of one cylinder surfaces among all. And we show that this, as the genus tends to infinity, this proportion decays as 1 over square root of J. We can also study the distribution of number of surfaces. And so we have a paper that shows that the number of cylinders of square-tile surfaces, this distribution converges to the Poisson distribution of parameter log 6G minus 6 over 2. It's a very strong convergence, and I won't extend on that, but it's a very nice result that you need to, which is really similar to the convergence of the number of cycles of random permutations. Actually, it corresponds to the convergence of number of cycles of random permutation, but not with the uniform law in some sense. Also, you have some theorem about the global separation, meaning that when you look at square-tile surfaces, you will get all singularities located in the same horizontal layer with very high probability when the genus tends to infinity. So you get a lot of results like this that distinguish between several kinds of square-tile surfaces. And the hope for the future is to show these results for odd strata. So I think the conjecture that I'm almost sure of this conjecture is that if you fix some odd set of singularities and you add a bunch of 1, and you let the number of 1 goes to infinity, so the genus goes to infinity, then you should get all these results. Really, you should get exactly the same result. But this is so far a conjecture. And you can make other more general conjecture by being, allowing more freedom on the parameters here, but I won't extend on that. And a really wild guess is that these intersection numbers will behave asymptotically similarly to the classical one. Okay, and I should say also that all these previous results use the result of Amol-Agarwal that studied the asymptotics of this intersection as G tends to infinity. So we really use this asymptotic result. So sorry, I think my time is off. And are there any questions?
I have a general one. Is there a hope to get something similar for abelian differentials?
So there are some work, there are some conjecture and some work for abelian differentials. So Duryev and I.Yakovlev have worked with the case of minimal strata. So abelian differential with only 1 0. I think Simon Barazer also is working of something for more general abelian differentials. So far, it's not done. Similar work is not done. So what is more painful with abelian differential is that if you look at ribbon graphs, if you can do the same story, look at square-tile surfaces, they decompose into cylinders, they are glued along ribbon graphs. But now, on your ribbon graphs, you have some orientation, additional orientation. If you want, it's a bipartition of the faces. And then you have some equality, you have some constraint on the lengths of the faces. So and this is, this is really more complicated to deal with when you want to compute. This asymptotics and this volume, this constraint is really more complicated. But yeah.
And what are the most complicated values of the degrees where you know explicit answers.
You mean, so I didn't hear the beginning. You mean, do we get explicit answers for the volumes or?
For the volume, yeah, for most complicated ones. How do they look like?
To which extent your formula is efficient? Is it possible to implement it on computer, for instance?
Okay, so no, our formula is not
have an explicit answer.
It's not the efficient way to compute volumes. We all have other ways to compute volume efficiently. But this is not an efficient way to compute volume. The only advantage of this formula is the hope to get asymptotic, to study, to differentiate between square-tile surfaces of distinct types, like for say one cylinder surfaces, etc., and study large genus asymptotics. This is the implementation of the formula we can do. We did it. But we couldn't go further than the algorithm of Eskimo-Kunkov, for instance, that are more efficient. So this is not the goal. The goal is not here to get explicit values. We already have some explicit values with other methods. The goal is really, at the end, to study really subtle properties of surfaces when the genus tends to infinity. So otherwise, this formula is quite of a nightmare to implement. It's like table graphs just goes like usually, and it's not efficient at all. Yeah, this is not the goal. In a way. That's right. That's right. You can, and this is what I mean by you can study really separately the contribution of this type of surfaces, this type of surfaces. Really, you have some of positive contribution, and the first the formula that we get for principal strata, the first application of this formula was the asymptotic of the volumes as the genus tends to infinity by Amola-Garval, and he was able to evaluate which terms contribute the most. This is, yeah, we did this kind of things too. But once you get this formula, you can evaluate which contribution is the more important, etc. You can evaluate things. So as Anton says, it's only sum of positive terms. Yes, so you can do estimations, but it's not for computing exact values. This is not nice.
Is there a topological recursion for this?
Probably. If there is some, so now the problem is these additional terms. So my guess is that for completed volume, there is some topological recursion because the formula has the same structure as the formula for principal stratum, and because
it looks like application of given action to some cosmological field theory. So this, as long as you see this summation over graphs, it is very well fit to the logical recursion. Specialty,
but specialist says that there should be something. Yeah. But yeah, again, the problem is these additional terms, these degenerations.
Yeah.
Well, it's more advantage than problem, I would say.
Okay. Why do you? What do you mean by that?
Because in a given dialection, these terms appear naturally. Just.
Mm-hmm. Yeah. Okay.
Okay.
Thank you very much. Very nice talk. Very clear, very useful.
Sorry? No. Thank you again.
That talk is very useful.
Okay. Thank you. Yeah, I'm sorry. I think it was a lot of things to say, but yeah.